The sun rose this morning. It will rise tomorrow. It has done this, without fail, for 4.6 billion years. Long before the first animal took its first breath. Long before the first ocean formed. Long before Earth existed at all. But here is the thing nobody thinks about on a Tuesday morning. It is dying. Right now, as you watch this, the sun is converting 4.2 billion kilograms of its own mass into energy every single second. Not burning it, converting it. Mass itself, actual physical matter, is disappearing and becoming light. Einstein's equation is playing out in real time, 93 million miles away, and it has been doing so since before the dinosaurs, before the first fish, before life itself. And one day, it will stop. What happens then is one of the strangest, most violent, most quietly beautiful stories in all of science. It involves forces we still don't fully understand. It involves quantum mechanics saving a dying star. It involves matter resisting gravity through sheer stubbornness at the subatomic level. And it ends with something invisible, cold, and nearly eternal drifting through the galaxy long after every living thing that ever existed is gone. To understand how the sun dies, you first need to understand what keeps it alive. The sun is not on fire. That is a common mistake. Fire is a chemical reaction. What powers the sun is nuclear fusion, something far more extreme. Deep in the core, where temperatures reach 27 million degrees Fahrenheit and pressure is almost incomprehensible, hydrogen atoms are being crushed together with enough force to fuse them into helium. This should not be possible. Two protons carry positive charges. Like magnets with identical poles, they repel each other violently. By all classical physics, they should never get close enough to fuse. The math says the probability is essentially zero. And yet the sun shines. The explanation is one of the strangest facts in science: quantum tunneling. At the subatomic level, particles are not just particles. They are also waves, smeared across a region of space in a quantum haze. That blur gives them a tiny probability, 1 in 10 collisions, of tunneling through the repulsive barrier and fusing anyway. The sun is so enormous and contains so many protons bouncing around so frantically that even that vanishingly small probability adds up to hundreds of millions of tons of hydrogen fusing every second. When 4 protons fuse into one helium nucleus, something is lost. The helium nucleus weighs slightly less than the 4 protons that made it. That missing mass, that tiny discrepancy, becomes energy. It becomes light. It becomes the warmth on your skin on a summer afternoon. This is the engine. And the fuel, hydrogen, is finite. The sun has been burning through it for 4.6 billion years. It has roughly 5 billion left. Right now, 2 forces are perfectly matched inside the sun. Gravity is trying to crush it inward. Fusion pressure is pushing outward. The sun exists in a constant standoff between these 2 forces, and the standoff has held for billions of years. But when the core runs out of hydrogen, fusion stops. The outward pressure drops. Gravity wins. The core begins to collapse. What happens next is counterintuitive. As the core collapses, it heats up, and that rising heat ignites something the core's collapse left behind. A shell of hydrogen just outside the depleted core. Hydrogen that was never hot enough to fuse before. Suddenly, that shell ignites. Here is the strange part. Shell fusion releases more energy than core fusion did. All that energy has nowhere to go but outward. It slams into the sun's outer layers, and the sun begins to swell. Slowly at first, then dramatically. Over tens of millions of years, the sun's radius grows to dozens, then hundreds of times its current size. Its surface cools as it expands. Hot plasma stretched thin radiates at lower temperatures, shifting from yellow-white toward deep red. This is why astronomers call it a red giant. Not because it glows red at first. Because it will. At its peak, the sun may expand to roughly 1 astronomical unit in radius. That is the current distance between Earth and the sun. the sun's surface will reach where Earth is now. Mercury gets swallowed. Venus gets swallowed. Billions of years of human history, every city ever built, every fossil ever buried, every ocean that ever existed on Mercury and Venus, all of it absorbed back into the star. And Earth? The honest answer is, we do not know exactly. Some calculations say Earth might survive, barely, sitting just inside the sun's expanded outer atmosphere. Others say friction from the sun's outer layers will slow Earth's orbit and pull it into a death spiral, dragging it inward until it vaporizes completely. But either way, Earth is already long dead by this point. Here is the darker timeline that most people do not realize. The sun does not stay the same, until suddenly it doesn't. It gets gradually, relentlessly brighter. Every billion years that passes, the sun increases in luminosity by roughly 10%. That sounds small. Over geological time, it is catastrophic. In about 1 billion years, 1 billion, not 5, that increased brightness will intensify Earth's water cycle. More evaporation, more rainfall. Rainwater carrying carbon dioxide will react with exposed rock at a faster rate than it does today, pulling CO out of the atmosphere. As CO levels drop, plants die. Plants are the base of almost every food chain on Earth. When they go, ecosystems collapse. Animals follow. Earth will become a desert world. Scorched, silent, stripped. About 500 million years after that, the last of the oceans begin to evaporate. Not quickly. Slowly, over millions of years, the water leaves. The sky thickens with water vapor, a greenhouse gas that accelerates the heating further. The remaining liquid water boils away. The planet bakes under a sky that traps heat and offers no relief. By the time the sun physically threatens to engulf Earth 5 billion years from now, Earth has been a dead, airless, bone-dry rock for billions of years. The planet we call home will be gone long before the star that gave it life swells to consume it. Back inside the dying sun, something extraordinary is happening. After the red giant phase begins and the core collapses, the helium that has been accumulating there for billions of years, the ash from all that hydrogen fusion, starts to compress and heat. The core shrinks. The temperature climbs. For millions of years, nothing ignites, because helium fusion requires temperatures far higher than hydrogen fusion does. The threshold is around 100 million degrees. The core creeps toward that number. Slowly, inexorably. And then it hits it. Helium fusion does not ignite gradually. It ignites explosively. In an event called the helium flash, the entire helium core detonates at once, a runaway nuclear explosion releasing more energy in a few seconds than the sun has radiated in millions of years. About 6% of the core is converted into carbon almost instantly. Then the explosion pushes back. The core expands. The pressure and temperature drop. The runaway reaction slows. The core finds a new equilibrium, smaller, cooler, now fusing helium into carbon and oxygen at a steady rate. The sun shrinks back down. It becomes slightly smaller, slightly bluer than it was at its red giant peak. This phase lasts about 100 million years. Then the helium runs out. The pattern repeats. Helium fusion stops. The core collapses again. The temperature rises again. The heat ignites a shell of unburned helium surrounding the core, just as it ignited a hydrogen shell the first time. The sun swells a second time, larger than before, more unstable, pulsating with giant waves moving through its outer layers. And now the question becomes, what comes next? What is the next fuel? The next step would be carbon fusion. But carbon fusion requires temperatures of around 500 million degrees. The sun does not have enough mass to compress its core to that temperature. It never will. The core has lost. There is no next fuel. There is no next ignition. The fusion chain that has been powering the sun for nearly 10 billion years ends here, with a core full of carbon and oxygen that will never fuse. Gravity has won. Or so it seems. Here is where something remarkable happens. Something that should not work, but does. As the core collapses under gravity with no fusion to stop it, the electrons inside it are being forced closer and closer together. Gravity is trying to crush them into the same space, and electrons refuse. This is not stubbornness in any human sense. It is a fundamental law of quantum mechanics called the Pauli exclusion principle. No two electrons can occupy the same quantum state. It is not a preference. It is not a tendency. It is a law of nature, with zero exceptions. When forced together, electrons generate a pressure, electron degeneracy pressure, that has nothing to do with heat, nothing to do with fusion, and cannot be overcome by simply applying more gravity. This pressure halts the collapse. The carbon-oxygen core stabilizes. It stops shrinking. Gravity pushes, the electrons push back, and the two forces lock into a permanent standoff, one that will hold not for millions of years, not for billions of years, but essentially forever. The sun will not become a neutron star. It will not become a black hole. Those fates require stars at least 8 to 20 times more massive than our sun. Stars like our sun are not massive enough to overwhelm electron degeneracy pressure. The electrons win, but while the core stabilizes, the outer layers of the sun are experiencing something entirely different. In its final stages, the sun becomes chaotic. Strong stellar winds blow outward. Giant pulsations move through the star. The outer layers, up to 30% of the sun's total mass, are pushed away from the core and drift outward into space. This is not an explosion. It is more like the sun slowly exhaling itself. Over thousands of years, the outer layers expand outward as a shell of gas. Then the hot core, now fully exposed, floods that expanding gas with intense ultraviolet radiation. The gas begins to glow. This is a planetary nebula. The name is misleading. It has nothing to do with planets. 18th century astronomers named these objects because they looked vaguely planet-like through early telescopes. In reality, they are the glowing remnants of a dying star's outer layers, lit from within by the exposed core. Our sun will create one. A stunning, expanding shell of multicolored gas. Blues, greens, reds, oranges, surrounding the compact remnant at the center. It will glow for tens of thousands of years before slowly thinning and dispersing into the surrounding interstellar medium. If any civilization exists in another star system close enough to observe it, the death of our sun will look like one of the most beautiful objects in the galaxy. What remains at the center is called a white dwarf. It is roughly the size of Earth. It contains most of the sun's remaining mass. Think about what that means for a moment. Earth's volume, but with the mass of a star. A teaspoon of white dwarf material would weigh several tons on Earth. Its surface gravity is roughly 300,000 times stronger than Earth's. There is no fusion happening inside it. No reactions of any kind. The white dwarf is simply the exposed core of the old sun, carbon and oxygen, held in place by electron degeneracy pressure, radiating the heat that was already trapped inside it. It glows intensely at first, hot enough to illuminate the nebula surrounding it. Then it cools, slowly, gradually, releasing heat into the surrounding space year by year, century by century. The white dwarf asks nothing of the universe. It demands no fuel. It sustains no reactions. It simply exists, cooling, radiating, fading. Over trillions of years, timescales that dwarf the current age of the universe, the white dwarf cools further and further. Its surface temperature drops. Its glow dims. The light shifts from white to yellow to red to infrared to nothing detectable. Eventually, it stops glowing altogether. This is a black dwarf, a cold, dark, inert mass. The size of Earth, but almost as massive as the sun once was, drifting silently through the galaxy with no light, no heat, no radiation of any kind. Invisible to any instrument that detects electromagnetic radiation. Here is the strange footnote to this story. No black dwarfs exist yet, not anywhere in the observable universe. The universe is only 13.8 billion years old. The cooling process takes far longer than that. Every white dwarf that has ever formed is still glowing. The oldest, faintest ones are cooling, but they have not reached black dwarf status yet. Our sun's black dwarf phase lies so far in the future that it is almost meaningless to assign a number to it. The universe as we know it will look nothing like it does today. Stars will have stopped forming. Most stars will have died. Galaxies will have scattered. The black dwarf that was once our sun will drift through a cold, dark, nearly empty universe, carrying inside it the carbon and oxygen that was once fused in its core. The same elements that, for a brief moment on a small rocky planet, assembled themselves into living things that looked up and wondered what would happen when the sun died. Step back for a moment and look at the full arc. A cloud of gas and dust, seeded by ancient supernovae, collapsed under gravity 4.6 billion years ago and ignited. For nearly 10 billion years, it fused hydrogen into helium, releasing light that made photosynthesis possible, that warmed oceans, that drove weather, that powered every living thing that has ever existed on Earth. Then it ran out of hydrogen. It swelled. It swallowed planets. It exploded its helium core in a flash that lasted seconds, but released more energy than the sun had radiated in millions of years. It shed its outer layers in a glowing nebula. It left behind a cooling, fading remnant smaller than Earth. Then it went dark. The sun is not special in any physical sense. The galaxy contains hundreds of billions of stars, and billions of them have already followed this exact path. The nebulae we see in telescope images, glowing shells of blue and red and green gas with bright cores, are other stars doing exactly what ours will do. The white dwarfs we detect scattered throughout the galaxy are other suns, already past the stage ours has not yet reached. We are watching the future of our own star. Everywhere we look, the atoms in your body were forged in the cores of stars that died before the sun was born. Calcium, iron, carbon, oxygen, cooked in stellar interiors over billions of years, scattered by supernova explosions, gathered by gravity into a new cloud, collapsed into a new star with planets, assembled on one of those planets into molecules that could replicate themselves, into life, into you. You are the byproduct of stellar death. And the star that currently keeps you alive is slowly, inevitably, progressing toward its own. The sun rose this morning. It will rise tomorrow. But every single morning, it has a little less hydrogen than it did the morning before. That is not a reason for despair. It is simply the most astonishing story in the universe, and we are lucky enough to be alive in the brief window when we can understand it.